last time I already started with one more example, namely this function here. Okay, so we are interested in finding a Taylor series representation or a power series representation of this function here. Now, if alpha is a non-negative integer, this is something we know already from high school. So in this case, okay, so we know already from high school that we can use the binomial theorem. In order to get a power series representation, and since Maclaurin series representation, power series representation is unique, so we know in this special case, the Maclaurin series of this function here is given by this here. Now, last time we discussed the general case, so where alpha is any real number. Now, and we saw already, okay, so we normally, if we have given a function and we have to find a power series representation, there is a general way to do this. This is what we have discussed last time. So normally you proceed in 3 steps. The first step is, since we are interested in a power series representation around the centered at the origin, we first look at the first step, we look at the Maclaurin series. So we determine the Maclaurin series of this function. In the second step, we discuss the convergence behavior of the Maclaurin series. And in the third step, we prove that the Maclaurin series represents the function on some suitable interval. And this interval might be a subinterval of the convergence interval. Okay, so for this power series, we saw last time already that the Laurent series, the Maclaurin series is given just by this series here, but suitable interpreted for the case where alpha is in R. So for this, in this case, you can define the binomial coefficient just as you have defined it for the case where alpha is a natural number. So this is the first thing, we derived the Maclaurin series. The second thing was, okay, we discussed the radius of convergence. So for this power series, we get that in general the radius of convergence is equal to 1. Okay, so we saw this last time, and then the last step in order to complete this program would be, okay, you prove you discuss for which x do you have this equality here. Okay, so last time I showed you the proof that this equality, using the usual Taylor's inequality, this was the usual approach we used for functions like sine of x, cosine of x, e to the x, and so on. Also here you can use the Taylor's inequality in order to prove or in order to show that this equality here indeed holds for all x which are positive and smaller than 1. So last time I showed you that this is true for x with x is larger or equal than 0. Yes, 0 is included, smaller or equal than 1. 0 is trivially, for 0 it's trivially satisfied. And we saw that last time it's not so easy by looking at just the Taylor's inequality. It's not so easy to complete or to extend this domain of x to something, because we hear the radius of convergence implies that this power series is convergent at least for x in this interval here. And what one would like to show is that this equality here holds for all x in this interval here. And we have seen that if x is negative, the approach we used last time doesn't seem to work. But for x for positive x, indeed it was possible. And I told you that in our textbook there is a very clever way in order to derive that this equality here holds for all x in this interval. This is if you look in section 11 point, this I think is 11.11. If you check 11.11, yeah, 11.11, there is one exercise which asks you to prove that that the function defined by this series here is equal to f of x on the on this whole interval here. Now, so maybe let's do this. So we know already from this discussion here that this series here has some function, has some value. So this series here defines some function g of x on this interval here. What we want to prove is that g of x is equal to f of x. Now, so we know that this series is convergent inside this interval here, at least. So maybe this series is also convergent at the boundary points, but we do not care at the moment whether such convergence takes place or not. But something we know is that, okay, if a function is defined like this here, if a function is defined as a convergent power series, we know that the derivative of the function has a power series representation as well, and you obtain it by term differentiation. So here n from 1 to infinity, and then alpha choose n, and then you have here n x to the n minus 1. Okay, and this power series representation is holds as well on the same interval. So we had the results which told us that this is true here. Okay. You see, if you look at this here, so you can simplify this. So you have the derivative of g of x is equal to. Now, if you look at the definition of the binomial coefficient, so you have alpha times alpha minus 1 times alpha minus n plus 1 over n factorial times n x to the n minus 1. Okay, so you can rewrite this. So you can one of the n cancels here. So what you have here is n minus 1 factorial. But here in the numerator you have n terms. So for instance, you can take out the last one. Then you can rewrite the rest as a binomial coefficient. So you have here, okay, this is the series n from 1 to infinity. So we take out the last one, and we cancel here the n. Then what we have is alpha choose n minus 1, and the last one, alpha minus n plus 1 x to the n minus 1. Okay, so you see you can write this as okay, the sum n from. So we take the series into two parts. So we have here first the part with alpha. So we have alpha, and then the series n from 1 to infinity, alpha choose n minus 1 x to the n minus 1 plus, minus, and the remaining series. Okay, this we can write as, if we have here minus, then this becomes here n minus 1. Then alpha choose n minus 1 x to the n minus 1. Okay, so you see that this here, what you see here actually is just g of x, because our definition of g of x was g of x is the value here of this series, because you can replace here. If n starts from 0, you can replace n minus 1 by n. Okay, so what you have here is g of x minus, and you can do the same here. So here you have the sum n from 0 to infinity, and then you have n alpha choose n, and then you have here x to the n. But actually here, I write it a little bit different. I take out an x and write it like this here. So you see that what you have here is the derivative of g of x. Sorry, I missed here an alpha. Okay. So you see, okay, we have this identity here. The derivative of g of x is equal to alpha times g of x minus x times the derivative of g of x. Okay, so this will give you that the derivative of g of x is equal to alpha times g of x over, and then you have 1 plus x. Okay, you see this is one of the exercises. Let me check it maybe. This is the exercise 19 in section 11.11, and what I have shown here is part A. Okay, in part A asks you to prove that okay, if you define g of x as the value here of this power series for x inside the the interval -1 to 1, then the function g of x satisfies here this so-called differential equation. Okay, so maybe I remind you what g of x was. So g of x was the sum function of this power series here. Okay, and now the trick is to define a new function h of x as okay, and you choose it 1 plus x to the minus alpha g of x. Okay, so why if I define such a function, this is now the part P of the exercise. Then if you compute the derivative, okay, so if we compute the derivative of this function here, so we have to use the product rule. So what we have is minus alpha 1 plus x to the minus alpha minus 1 g of x plus 1 plus x to the minus alpha, the derivative of g of x. But you see the derivative of g of x you can replace by this expression here. Okay, so we know that this is minus alpha 1 plus x to the minus alpha minus 1 g of x plus, and for the derivative we just plug this in what we have just shown. So alpha 1 plus x to the minus alpha minus 1 g of x. So you see those two terms cancel. So what you get is 0. Okay, and this holds for all x in this interval. So this function h of x, the derivative of this function h of x is 0 on this interval. So it must be a constant. Okay, so h of x must be a constant on this interval here. But this constant is easy to compute because you notice h of 0, what is h of 0? Is 1 times g of 0. And g of 0, you just plug in here, you see equal to 1. Okay, so h of 0 is 1. So from this you get that the constant must be equal to 1. So you see that okay, what you get is 1 plus x to the minus alpha g of x is equal to 1. Okay, but this means that g of x is equal to 1 plus x to the alpha, which is f of x. Okay, finished. You see, but you see this is very tricky. Okay, and this of course just works for this function here. So you see what we want to prove is that g of x. So we have shown that this power series is convergent, is the Maclaurin series of this function, and convergent on the open interval from -1 to 1. Okay, so we call this function g of x, and we want to prove g of x is equal to f of x. Now what we do is, okay, we first get some properties of g of x. So the derivative satisfies this here, and this, and then we define this function. Okay, if you just look at what you want to prove that this is equal to f of x. So you want to prove that this is equal to 1. Okay, then it becomes clear why we are looking at this function here. And for this, by using this property, you can prove that this function indeed is equal to 0, and then you use, and then you can you use results from last semester, and you get that h of x is a constant, and you compute the constant. That's it. You see, this is much easier than using Taylor's inequality in order to prove that the Maclaurin series of this function, okay, represents the function, but of course it's pretty tricky, and you need some experience in mathematics to come up with such an idea. Okay, but this is another way to prove that the Maclaurin series represents the function. But the general way we use normally is Taylor's inequality. Okay, Taylor's inequality gives us bounds us the error, and gives us a tool in order to prove that the error indeed tends to 0 as n tends to infinity. Okay, and this completes the proof that 1 plus x to the alpha is equal to this series here, something which is, this is called the binomial series, and this extends the binomial theorem you have learned already in high school. So this is an important result. Okay, so the main message is that, okay, this function is equal to this series alpha choose n x to the n for x in this interval here. That's what we just proved. Okay, so you can represent this function by this power series. You see, this, for instance, includes some cases we have discussed already previously. For instance, this includes the case where alpha is equal to -1. Alpha is equal to -1 is geometric series. Okay, but if you check this, okay, this will be equal to 1 plus x squared plus 1 minus x plus x squared minus x to the cube, and so on. Okay, so this includes actually some of the previous cases, but this is more general because you can for alpha also choose 1/2 or -1/2, and so on. Now, something which would be interesting, which is also mentioned in our textbook, is okay. This series, okay, has radius of convergence 1, but this doesn't necessarily mean that this is the interval of convergence. Okay, but so what you have to check is the endpoint +1 and -1. Actually, checking the endpoints here for this series is not so easy. In our textbook, it's mentioned. Okay, it can be proved that the interval of convergence here of this series, the binomial series, so the interval of convergence okay, is the whole interval if alpha is larger or equal than 0. Then, I don't remember whether the left or the right endpoint is included. Then this interval here if alpha is larger than -1 and smaller than 0. And if alpha is getting even smaller, so if alpha is smaller or equal than -1, then we have the open interval. So the interval of convergence of this series here, okay, depends on the alpha. So depending on the range of alpha, it changes. But this actually is not so easy to prove. Okay, if you can try to check it, it's not so easy to prove that this series here is convergent as well at these points here. And even more is true. This identity here, what you see, okay, this equality, which we just have proved inside this interval, okay, for alpha is larger or equal than 0, also holds for -1 and 1, and for in this case also holds at 1, and in this case also holds at here we do not have here. It just holds on the open interval. So you see that the identity here, or the domain on which the Maclaurin series represents this function here, is equal to the interval of convergence. Okay, it can be proved, but this is just to make this theorem complete, and it's mentioned in our textbook as well. So actually, this identity here holds whenever this series is convergent. Okay, which in this case includes the two endpoints. Okay. Now, maybe let's just look at one example. In our textbook, you find something like this here. 1 minus 4 x, similar to this example here. In the textbook, maybe 4 minus x, but doesn't matter. Okay, so if I have something like this here, then you can write this as 1 minus 4x to the minus 1/2. Okay, and so if you are asked to find the power series representation of this function here, it's just a special case of the binomial series. So what you have is, okay, this series n from 0 to infinity, and then you have minus 1/2, choose n, minus 4x to the n. You see that this is one example in our textbook. This actually can, in our textbook, the final form is like this here. I think in our textbook is 4 minus x, I don't remember, more or less this one. But actually this can be kind of simplified if you do not like this one. So it can be brought in a more easier form, in a more, not really easier form, but a form which looks better than this one. Okay, so what is the definition of this binomial coefficient? Minus 1. Then minus 1/2 minus 1, and you go on until minus 1/2 minus n plus 1 over, and here you have n factorial, and here you have minus 1 to the n, 4 to the n, x to the n. You see, what we can do is okay, first of all, because we have here n minus 1, okay, so we can multiply minus 1 to every of those factors you see here. Then you get here 1/2, you get 1/2 plus 1, and here you get 1/2 plus n minus 1. Okay, and then you can take a 1/2 out from every factor. Okay, so if you take a 1/2 out, because you have here n factors, then what you get is, okay, the first one becomes 1. Okay. The second one becomes 3. And you go on like this. And what is the last one? This is the important one. So you take out 1/2. Then you have minus 1 minus n plus 2. So you have minus n plus 1. So you have 2n minus 1. Okay, so the last one is 2n minus 1. Okay, I just take 1/2 out from every factor, and then I multiply everyone with this minus 1 here. Okay, over n factorial 4 to the n, x to the n. Okay, so actually this one cancels with this one. Then we have just 2 to the n left here. So what we have is 1 times 3 times 2n minus 1 over n factorial. And here we have 2 to the n, x to the n. And now you see, because here all the evens are missing, okay, so I multiply all the evens in the numerator and multiply also in the denominator with all the evens. Okay, so what I get here is this series n from 0 to infinity. So I multiply this here with 2 times 4 times 6 times and so on times 2n. Then the denominator becomes 2n factorial. Okay, and here I have also to multiply with 2 times 4 times 6 up to 2n. So what I multiply here is 2 to the n times n factorial 2 to the n, x to the n. Okay, so you see that this one also cancels out. Okay, and what is left here is 2n, choose n, x to the n. Okay, so it's kind of can be. You find in our textbook this is the final expression. Okay, but this can be simplified because you maybe agree that this looks more easy than this one. Okay, but of course this is already the answer if you are asked to find the Taylor series. This is actually an important example, and you will learn it in other classes because it's related to combinatorics. Okay, so any questions to this? But just an example. So you see how to apply this binomial theorem. This is a quite convenient result. But as I said, sometimes the result you get, you can find it more easier by using other approaches. Maybe let's look at one such example. For instance, if you have this function here, f of x is equal to 1 over 1 minus x squared. Okay, also this, you can interpret this as a special case. So if you are asked to find the power series representation, you can interpret this as a special case of the binomial theorem. So what you get here is, okay, the series n from 0 to infinity. Then you have here minus 2, choose n. And then you have minus 1 to the n, x to the n. Okay, so also this can be simplified. Actually, this already would solve the example if you are just asked to find the Taylor series expansion. But this can be brought in a more simple form, using a little bit similar reasoning to the one you just have seen, you just saw. So what is the denominators? Minus 2 times minus 3, and you go on like this. And the last one is minus 2. Sorry, minus n plus 1 over n factorial minus 1 to the n, x to the n. Okay, so you see that, again, you can multiply all of them. Because you have here exactly n minus 1, you multiply, and here you have n factors. You multiply every factor with minus 1. Then what you get is okay, so you see that the last one is n plus 1. So what you get is n plus 1 factorial over n factorial x to the n. Okay, so what you have is n plus 1 x to the n. Okay, or you can write this as the sum n from 1 to infinity, and then you have n x to the n minus 1. Okay, and you see that this here, okay, you see from here, because maybe I just write that this is equal to this here. Okay, this is not really new for us. Okay, so we do not need the binomial theorem for this. Another way to do to derive the same result is you start with this function here. You notice that this function has this power series representation, and you take derivatives on both sides. Okay, it's maybe more easy. If you take derivatives on both sides, what you get is 1 over 1 minus x squared is equal to, and here, okay, the same result, but more quicker. Okay, so you see that in order to find the power series representation of this function here, there are two different ways. One is you use the binomial series, okay, then you get this result here, but you can also use, you just observe that the given function is the derivative of this function here. Okay, so you already know this is something you know. You take derivatives, and that's it. Okay. So you see that this is sometimes helpful if you for instance, maybe these are examples you have seen already in high school. So if someone asks you, okay, find the sum of the series, okay, then you see that in high school, maybe what you have done in high school, maybe some of you have seen this. So you look at the partial sums of the series, and then you multiply suitable, okay, and take the difference of the original series of the original sum, okay, and you will get an expression. It's somehow similar to how you prove this formula here. Okay, can be applied for this as well here. Okay, you know this from high school. But now, if someone asks you, okay, find the sum of this series, you have a much easier way to do it. Okay, you just observe. Okay, so first of all, you generalize the problem. Okay, you say, okay, the 2 to the minus 1, I replace it by x. Okay, so first you generalize the problem. Okay, now you take out an x. Okay, and you see this power series, okay, you can obtain by taking the derivative of this one. Okay, so you see that this is x over 1 minus x squared. Okay, so what you have to do is, okay, in order to find the sum here, okay, you just plug x is equal to 1/2 here in, and that's it. Okay, so this is a kind of different way to now to compute the value of such series. But more, of course, you need a little bit of experience. But once you have the experience, it's pretty easy. Okay, you can think about. Okay, so if you wanna, for instance, if you wanna have this one, okay. So again, the task is, okay, find the sum of this series. Of course, you can use high school methods. Okay, maybe after some thinking, okay, you can derive the sum. But you have now a more easy method. So what we do is, okay, we have to look at this series here. Okay, I take out x squared. And I observe that this is the second derivative. This is I get this series if I differentiate this twice. Okay, so I get that this is equal to x squared. Here is already the first derivative. The second derivative is 2 times 1 minus x to the cube. Okay, and now I plug in 1/2, and I get the sum of this, the value of this series here. Okay, so the main message is you do not need the high school methods anymore. Okay, computing the value of the series is not tricky anymore because we know already enough about series. We have gathered quite a lot of results which allow us to quickly compute such series. You see also, because you already also this series is now no problem for us. Let's say this one. Okay, because you more or less have just to add this one to this one and you get this one. You see, it's a different way to compute the values of such series. Okay, so sometimes if you've given a series, okay, this actually is the main thing I want to say. If you have given a series, okay, and you are asked to find the value, okay, it's not always the best thing to look at the partial sums. Of course, it's the most natural thing to look at the partial sums and try to sum them up and take the limit. Okay, but it's not always the most easiest thing to do. Okay, sometimes it's better to, okay, given a series, try to find the Maclaurin series, okay, which evaluated for certain x, okay, gives your original series and compute it like this. It's another method. Now, just in order to finish this chapter on series, the first thing I would like to mention is, okay, we saw now a couple of examples for power series representations of given functions. So we started out with 1 over 1 minus x. Then we looked at functions like the arctangent of x. We already found the power series representation of e to the x, sine of x, cosine of x. We saw the power series representation of 1 plus x to the alpha. Now, in all those cases, you might have observed that if we carry out a 3-step program, okay, so the first step was to find the Maclaurin series. The second step was, okay, discuss the convergence behavior of the Maclaurin series. We saw in all the cases, okay, for instance, sine of x, the radius of convergence of the Maclaurin series infinity, and we saw that the Maclaurin series represents the function for all x. Okay, so actually, in all the examples we saw so far, we had the phenomena that the domain on which the power series representation holds, so the domain of all x, the set of all x for which the function is equal to the Maclaurin series is equal to the interval of convergence of the Maclaurin series. Okay, so in all of the cases, okay, so you have a function f of x, you compute the Maclaurin series. Okay, and we saw that this identity here, okay, always holds for all x where this series here is convergent. All the examples. We just saw the as one of these special cases, the function 1 plus x to the alpha. So in this case, we saw that whenever this series is convergent, you have this equality here. Okay, so this kind of raises the question whether the third step is really necessary. Okay, is it really necessary to? So once you have figured out the domain of convergence of the Maclaurin series of f of x, is it not always the case that for all those x where the Maclaurin series makes sense, okay, it is equal to the function. And since we have spent time for every example proving it, you might easily guess, no, it's not always the case. So there are indeed functions where you have, for the Maclaurin series, some domain of convergence, but this equality here does not hold whenever the Maclaurin series converges. Now, the most famous example, and this is also one of the examples in our textbook, is this example here. So we have this function. Okay, you might imagine that such a function must look a little bit exotic. It doesn't look too exotic. So you define a function as e to the minus 1 over x squared if x is not equal to 0 and 0 if x is equal to 0. Okay, we are interested in the usual problem, find the power series representation of this function here, centered at the origin. Now, okay, so the first step is to find the Maclaurin series. For this, we have to find the nth derivative. So we see that f of 0 is by definition 0. Now let's compute the first derivative. Okay, so you see, because the function is defined like this here, we have to go back to the definition of the derivative. Now, by definition, this is the limit h tends to 0 of f of h minus f of 0 over h. Okay, so we have but f of 0 is by definition 0. So if you plug this in, what we get is the limit h tends to 0 e to the minus 1 over h squared over h. Okay, now this limit as h tends to 0, okay, this tends to infinity, so this tends to 0, so we have 0 over 0. So what we are going to use is the L'Hopital. But actually for this one, okay, you will discover it's not so easy to use the L'Hopital. You shouldn't use it in this form, okay, because if you differentiate this one, what do you get? 1. This would be okay. But if you differentiate this one, what you get is e to the minus 1 over h squared times, and then you get something minus 2 over h to the cube. Okay, so essentially you get the same expression, but h replaced by h to the cube. So you win nothing if you use the L'Hopital like this. So here this is an example where using the L'Hopital is a little bit more tricky because you have to write it as this here, 1 over h over e to the 1 over h squared, and then use the L'Hopital. Okay, so you have infinity over infinity. So this is equal to the limit h tends to 0. If you take the derivative here, what you get is minus 1 over h squared. And if you take the derivative here, what you get is e to the 1 over h squared. And then you have minus 2 over h to the cube. Okay, so things become easier. Namely, what you get is h times h to the minus 1 h squared. And now you do not have an indefinite form anymore, because if you plug in, here you have 0, here's 0 as well. 0 times 0 is 0. Okay, so what you have is 0. Okay, so the first derivative, 0 as well. Actually, it's easier to see, right? Because you look at this here, you see that what you have here is, as h tends to 0, this tends to infinity, but e to the minus tends to 0 very, very quickly, much quicker than this function. Okay, so what you should get is 0, because this function should win the race between those two. This would be another way to see of seeing things, but more heuristic. So the first derivative is 0. And now you go on like this. Of course, it becomes rather complicated. compute higher derivatives. Okay, but it's not so complicated to show that all the derivatives, I shouldn't write it like this. So if you go on like this, you will see the nth derivative is equal to 0 as well. So all the derivatives are 0. Okay. So what is the Maclaurin series? So the Maclaurin series is by definition this series here. So the function of f, the function f differentiated n times, evaluated at 0 over n factorial x to the n. Now, since they are all 0, okay, this function is very easy, 0. Okay, so you see the Maclaurin series of this particular function is very easy. The Maclaurin series is 0. So the Maclaurin series, in particular, has a radius of convergence which is infinity. Okay, but you see, the Maclaurin series does not represent the function, just in one point, namely x is equal to 0. But this must, of course, in this point, if you look at this, this identity is always true, okay, at the point at which the power series is centered. Okay, so you see that here you have a function where the Maclaurin series is convergent everywhere for all x, but represents the original function just in one point. Okay, so you should understand, if you understood what I said last time, then you should understand that this example shows you that this example is very different from everything we have discussed so far. Namely, this is an example where where this equality here does not hold for all x, where this series here makes sense. Okay, this equality just holds in one point, x is equal to 0. So it's pretty different from the other ones. I think this example is going back to at least Riemann. And this is one of the famous examples which shows that the Maclaurin series does not necessarily represent the function, except in the trivial point at which the Maclaurin series is centered. OK, so any questions to this? Also, this is one of the examples in our textbook. You can complete it by showing that for all n, the nth derivative at 0 is equal to 0. OK, so this essentially concludes what I want to say about Maclaurin series expansion. Of course, there would be much more to the topic, and you will learn this in other courses. This is something, power series representations of functions is something which is very, very important, and you will encounter it throughout your studies in all other subjects, which are related to mathematics. Now, I showed you already some reasons as for why we are interested in finding a power series representation of a given function. I showed you that, okay, for certain integrals we could not solve last semester, like the integral e to the minus x squared dx. We are now able to find an to solve it, or in other words, we are now able to find an antiderivative of this function, but expressed as a power series. And this is in particular useful, as we have seen last time and the last few times, in order to compute integrals. Now, some definite integrals which we wouldn't be able to compute numerically, which we wouldn't be able to compute precisely. Now, another reason for power series representations is computation in general of functions. So, for instance, if you want to compute e to the x, okay, or if you want to understand, okay, how does the calculator compute e to the x? Because you know, okay, if you fix some x 0.01 and you plug it into the calculator can compute it. But how does the calculator do it? Now, we saw already that this function here, e to the x, we have a power series representation which is of the following form, and this holds for all x in R. Okay, so if you have a general function f of x, which you can represent by a power series. So let's say an x minus a to the n, okay, then you get a natural way to compute the function f of x. So what you do is because this is a series, by definition, you can replace infinity by n and take the limit as n tends to infinity, and you get this function f of x. So what you will do is, okay, you look at the Taylor polynomials. Maybe I just replace this by the Taylor series. Anyway, if there is a power series representation, it must be the Taylor series. So what you do is, okay, you look at the nth Taylor polynomial, which is just the first n plus 1 terms of this series. And we know that, okay, the Taylor series has to converge to the function f of x as n tends to infinity. Okay, and this gives you a method to compute the functions like e to the x, because it's certainly much easier to evaluate a polynomial. This is something which the computer can do, but the computer cannot compute e to the x unless you write a program. Okay, but multiplications and summation is easy. Okay, so you see that here this is a polynomial. A polynomial is easy to evaluate, and what we do is if we have to find f of x for a certain x, okay, we just replace f of x by the nth Taylor polynomial and evaluate this instead of f of x. And this actually is what the calculator is really doing. So the calculator is really, if you have to compute e to the x, if you compute e to the x for some value of e, what the calculator does is it evaluates that nth Taylor polynomial instead of it, where the n is chosen large enough such that the error is small. Okay, this is important. Now, you see that maybe for if you look at the function e to the x for two values, (0.2 and 3), and you compute the Taylor polynomials instead of the function. So what you have here is 1.220000. Then here you have 1.221400. Here you have 1.221403, and the remaining ones do not change. But for this one, if you choose x is equal to 3, what you get is 8.50000. Here you have 16.375000, 19.412500, 20.279665, and 20.979. Wait, this is not correct. 09152, and this is 20.079665. You see, maybe it's worth it to look at some examples. To look at one example, you see that if you choose x is equal to 0.2, okay, you do not have to choose a very high n. Okay, you already get a very good approximation. Of course, from here you do not see the error, okay, because this is the real value. So you do not see actually what is the error between this value and the precise value e to the 0.2. Okay, but normally you can be pretty sure that the digits like this, which do not change anymore, okay, are correct. That's why they do not change anymore. Okay, so you see that starting from n is equal to 4, all the digits do not change anymore, so they are correct, and they are indeed correct. Okay, so you see if x is equal to 0.2, okay, you do not have to choose. It's not necessary to choose n very large. You already get a very good approximation for the function f of x. But if you choose x is equal to 3, okay, you see that the convergence to the value e to the 3 is much slower, because you see that if we once more apply the general rule that the digits which do not change are correct, and we see that here maybe the first 3 digits might be correct. Okay, the rest is changing, is still changing. So here the conversion is much slower. The reason for this is because our power series is centered at 0. Okay, so if you are close to 0, you will get quickly a good approximation. But if you are too far away from 0, the conversions will be much slower. So if you have to compute, for instance, this value, okay, you're not going to use this one, okay. You will use the power series representation centered at some other point, okay. So you see that if I say that the calculator uses this kind of approach to compute e to the x, okay, there are still many questions left, okay. So how does the because the calculator I give the calculator a value like 3, okay. So which power series, okay, centered at which point, okay. And this is the first question. The second question is, okay, how does the calculator know how to choose the n such that you get a certain precision, okay. So how about the error? Now for the error we have some tools, okay, in order to estimate at least the error. The general tool we have, Taylor's inequality, will estimate the error. So if we replace a given function f of x by the nth Taylor polynomial, normally we can bound the error by using Taylor's inequality. The situation is very easy if we have a series which is alternating. Because if we have a series, if the Taylor series is alternating, okay, then we know that the error is just bounded by the first term you drop. Okay, so this situation is very easy. So for instance, if you look once more at the power series or Maclaurin series representation of sine of x and cosine of x, you see those series are alternating. Okay, this makes it easy to, if you have an alternating series, it makes it very easy to estimate the error because it's just bounded by the first term you drop. Okay, so for sine of x, approximation is easy, is in some sense easy because you can easily bound the error. So maybe let's look at one example. You should note here something. If you look at here at the nth Taylor polynomial, okay, if you look at the first Taylor polynomial is nothing else but the tangent, okay, and the nth Taylor polynomial, okay, is a polynomial of degree n, which coincides with the function at the point a in the function value and the first n derivatives, okay, by this here. Maybe you remember last semester we had a exercise. One of the additional exercises was to find the polynomial which is identical with the original function in the function value at some point a and in the first n derivatives. It's actually this exercise told you to find the nth Taylor polynomial. And the nth Taylor so the nth Taylor polynomial, you kind of understand, if you see this property, you kind of understand how the approximation takes place. Namely, what you require is that the function, the polynomial with which you approximate the function, is, of course, what you require is that the polynomial is getting closer and closer to the function. But the way you choose the approximation is, okay, you choose the polynomial such that the polynomial is the same at the point a, because the expansion should be centered at a, so it should be good if x is very close to a. So the polynomial at the point a should have the same function value, and the first n derivatives should be the same. That's the way how you choose the approximation. This is the approach taken by Taylor series expansion, power series representations. Okay, so let's look at one example. So for instance, the sine. Okay, so for the sine of x, we know already the Maclaurin series expansion of the sine of x starts with x minus x to the cube over 3 factorial plus x to the 5 over 5 factorial. So let's assume we use this polynomial in order to approximate sine of x. Now, so how good is the error? Or how, not how good. So bound the error. If, let's say, we are in the following range for x, so x between minus 0.3 and 0.3, and when is the approximation? Accurate within 0.00005. Okay, so this is not complicated for us now. So what we have to do is, okay, we have to bound the error which you get if you replace sine of x by this here in this range here. Okay, but for the error we use the notation. Okay, so here we have. Okay, so this was the notation we used for the error, sine of x minus the first few terms of the here the first 5 terms of the Taylor series expansion. Okay, because this series here, alternating series. Okay, so we know that the error smaller equal the first term you drop. So the first term you drop is the absolute value actually of the first term you drop. So this one. Okay, so in this range here, what you get is smaller equal. You replace it by the largest, so you have 0.3 to the 7 over 7 factorial. And if you compute this, then you get this is around 4.3 times 10 to the minus 8. So already very good. Because for the calculator, I don't know how many digits does the calculator have, 8 or 9? I don't remember. I haven't used one for many years. How many does it have? For 9 or 12? How many? This may be many. Maybe 9 or 12. I don't remember. I haven't used the calculator for many years, so I don't know. So you see that here you know how to choose. Okay, how the calculator has to choose, how large the calculator has to choose the n here, such that all the digits which are displayed are correct. Okay, this is maybe not good enough, but if the range is a little bit smaller, okay, then this is good enough. Okay, so for this range, then the calculator can just replace sine of x by this polynomial and gets the same value, because anyway the other digits are not displayed on the display. Okay, and for the second question, okay, you just choose the same. You use the same pound here, and you. So the question now is, okay. So for the second question. So now we have an error bound. So what we have is this must be smaller equal than 0.00005. Okay, and from this you can compute the range for x, and what you get is, of course, because you see that in this range for x, okay, you already get a better precision. So this will be a larger range. So what you get is the absolute value of x is smaller than 0.821. Okay. And you see, this is what you get by using the error bound for the alternating series, okay? Because this is the alternating series, which makes it very convenient here to bound the error. But if you use Taylor's inequality, okay, you would just get the same bound. Because what do you need for Taylor's inequality? Actually, this is equal to R6 because the next one is 0 plus 0 x to the 6 over 6 factorial. So for Taylor's inequality, you need a bound for the 7th derivative. But since you are handling here sine, and derivatives of the sine are always bounded by 1, you just get the same bound here. Okay, so you get the same bound by using Taylor's inequality as well. So you see that, okay, so if you choose the x small enough, okay, then the calculator can replace sine of x by this polynomial here. And for other ranges, okay, normally what you do is, what the calculator is doing is, okay, using some, there are many identities, okay, for trigonometric functions where you can replace, of course you just have to implement sine of x on an interval from 0 to 2 pi, because if it's larger, then you first replace the x, the input, okay, by something which is in the interval 0 to 2 pi because of periodicity. So it's just necessary that the calculator has a good calculation, has a good approximation at the interval 0 to 2 pi. Or if you have symmetric around 0 from minus 2 pi to 2 pi, okay, which would be certainly possible with this approach here. So this should roughly explain how the calculator is doing computations. Now, since you have this tool at hand, you can throw away the calculator, and from now on you can do all the calculations by hand because you know how to do it. Even for complicated functions like sine of x, cosine of x, or even more complicated functions like arctangent and so on. Also for square roots, it would be possible to use such an approach. And in, I think in our textbook you see an example for the third root of x. Of course, the square root of x does not have a Maclaurin series expansion. Because if you take the first derivative and evaluate it at 0, it would be infinity. And for a function to have a Maclaurin series expansion, what you need is that all derivatives of the function, the nth derivative at 0, exist. But this is not true for f of x is equal to square root of x. So the square root of x does not have a Maclaurin series expansion. But it's no problem for the calculator because it's enough to have, of course, the square root of x has a power series representation that's centered at another point, which is larger than 0. If you're interested in more applications of power series representations, and there are many, and you will see many of them, or maybe you have seen already some of them in other classes, you find also more in our textbook related to physics, but I'm not going to discuss them since my knowledge in physics is very limited. Okay, so but in you have seen in physics already, I guess already in high school, that the sine of x is very frequently for small x replaced by x, something which just tells you, okay, you replace the sine of x by the first Taylor polynomial or by the tangent, okay, and you can make this approximation better and better if you replace it not by the first Taylor polynomial but by the third or fifth or seventh and so on, so like we have seen here. Now, the next thing which this actually finishes the chapter on series. There will be much more to say about series, and there are own books. If you go to the library, you will find own books which are just dedicated to the topic of series. So this is not everything, but this is enough for the moment. So we will now turn to a completely new topic. Now, the next chapter which I should discuss is chapter 12. And from chapter 12, we have to discuss the first 7, 12.1, 12.2, 3, 4, 5, 6, 7. The first 7 sections. I guess most of it is known. So from 12.1 to 12.3 should just be a review. This is what you have learned in high school. This is what I was told. But I guess also chapter 12.4 and chapter 12.5 you have learned in high school, which is the cross product. I guess this is common in high school, right? The cross product of vectors. The cross product and chapter 12. What is 12.5? I don't remember. Equations of lines and planes. I guess also this is you have learned in high school. So maybe we can just very quickly review it, just to fix some notation. This is something which is important. So what we are talking about are now vectors, something which you have briefly discussed in high school, and I guess which you have discussed in details in linear algebra, because linear algebra is the theory of vector spaces. Now, we are talking here about, I'm not sure whether in linear algebra, I guess you have defined what the vector space is. So what we are talking here about a special situation, namely 2- and 3-dimensional space, which is more easier. Now for the 3-dimensional space, we normally fix the standard coordinate system, the Cartesian coordinate system. And those axes you see here are called the coordinate axes. You have the 3 coordinate planes. I'm not sure whether last semester we have terminology which you might have not heard before, but which we will need, of course, is octant. So normally, octant is the same as quadrant in the plane. So in the plane, normally the coordinate system divides your plane into 4 quadrants, whereas in the space you have 8 octants. This octant here is normally called the first octant. So you have also an order, but normally I will say which octant if we discuss octants. Now, you see, you can read on your own section 12.1 because this is very trivial. Now, section 12.2 is just the introduction into vectors using the naive approach which you have learned in high school, namely a vector is something which has a direction and has a length, and you can shift it, and if you shift it, it doesn't change. So this is the very naive way in defining vectors. Normally what you do next in high school is you define how to add 2 vectors, and then you define the scalar product, and then you know that if the set of all vectors together with the scalar product and the addition is satisfying the following properties. Maybe I just copied this on the blackboard because this is, of course, something important. So this also shows you how I'm going to denote vectors. So normally I denote them by bold letters. And this here, this symbol is different. This is not. This is different from the n-dimensional space. This is the vector space in n dimensions. So it's a difference. And I have scalars. Okay, so you have a couple of properties. A plus b is equal to b plus a. You have a plus b plus c is equal to a plus b plus c. You have a plus. You have one special vector, 0 vector, which has length 0, no direction. It's equal to a. It's equal to the 0 vector. You have c times a plus b is equal to c times a plus c times b. You have c plus d times a is equal to c times a plus d times a. And you have cd times a is equal to cd times a. And you have the last property, 1 times a is equal to a. And I guess you learn in linear algebra that these are the defining properties of a vector space. So normally you can forget about errors, and you can forget about so you can completely forget about errors, and you can say, okay, every set where you have 2 operations, an addition, and you have a multiplication with elements from the real numbers which satisfy those properties, called a vector space. I guess this is the definition in linear algebra, right, for a vector space. Yes or no? Yeah. So, so you know that you have in linear algebra you are discussing a much more general situation, and the vector space I normally denote by Vn, which is different from this set here, because the vector space also carries structure. So you have an addition, you have a multiplication, and so on, which you here this is just a set, so it's different. So normally I use this notation here in order to denote the n-dimensional vector space, which you can identify with r to the n. Now, but since we are discussing a more simpler situation, namely r to the n, things are getting much more easier because you can introduce components for the vectors in a very natural way. You just shift the vector into the origin, and you represent the vector by the point which you get if you shift it into the origin. Now, this is just something I also have to stress. So normally, if I talk about a point, okay. So if I have to talk about a point, then I will denote the coordinates of the point, okay, here by brackets. But if I talk about a vector, I will denote the components by this here. It's of course different, okay, because this here means I use a special basis and a special parametrization of every vector. And what I use as the basis are the standard basis vectors, which are normally denoted by, so this one is I, and this one is J, and this one here is K. Okay, so in the three-dimensional space, also in the two-dimensional space, I have a basis, but in the three-dimensional space, okay, I have these three special vectors, okay, which form my standard base. And using this, I can represent every point in the three-dimensional vector space as a sum of scalars multiplied with the standard basis vectors. So this is just in order to fix notation. Okay, and once you introduce coordinates, everything is getting, of course you can rewrite the addition, scalar multiplication, and so on, everything in terms of coordinate, also computing the lengths by using the usual Pythagorean theorem is getting easy. The next thing you normally do in high school is you define the dot product. Okay, so if you have two vectors, let's say in this three-dimensional vector space over the real numbers, and you introduce coordinates. So this one is A1, A2, A3, and B is equal to, okay, you have the coordinates B1, B2, B3. Then what you do next in high school is, okay, you define the inner product or the dot product as this sum here. So this has different names, dot product. But the much better name actually is inner product. And also this inner product satisfies a certain properties. Now, inner product is something which you can define more generally on the vector space. This is just for the three-dimensional vector space. And you know that the most important thing about this inner product, two things are very important about the inner product. The first thing is it is an easy tool. It allows you to check whether two vectors are orthogonal or not. If this is a vector and this is a vector, then normally you define this angle here, theta. Of course, you have two different choices for the theta. This would be one, and this would be another one. But you choose the one which is between 0 and pi. This is the angle between those two. And if theta is equal to pi half, then A and B are called there are different names, perpendicular or orthogonal. Normally I write that A is orthogonal to B. I use this symbol. And using the inner product, it's very easy to prove that the two vectors are orthogonal if and only if the inner product is equal to 0. So this gives you a very easy tool to figure out whether two vectors are orthogonal. The reason, as you know, is this formula, namely the inner product can be easily computed as the length of A times the length of P times the cosine of this angle here. Okay, and you see that actually this definition is not complete because I have to say what happens with the 0 vector. The 0 vector by definition orthogonal to any vector. Okay, then this is really true here. Okay, so the first important thing about the dot product is that it gives you a very easy tool to check whether two vectors are orthogonal or not. You just have to compute the product, the inner product, and check whether it's 0 or not. So in some sense, the inner product, also looking at this formula tells you that the inner product tells you to which extent is a measure which measures to which extent does do two vectors A and B point in the same direction. Okay, because equal to 0 if they are completely opposite, and if they are, and this is largest if they are in the same direction or have opposite directions. So it somehow tells you is some measure how far are two vectors away from being orthogonal. Okay, so this is the first important property of the inner product. The second use of the inner product is, as you know from high school, is in terms of projection. It's a very convenient tool in order to do projections. Also, this is more or less stemming from this formula here. You see that normally, okay, if I have two vectors, A and B, okay, then the vector which I get if I project A onto B is called the vector projection. So this vector here, C, is called the vector projection of A onto B. Now the textbook has a funny symbol for this. Actually, let's replace it. That's the same as in the textbook. So C is equal to, so we use this notation here sometimes. This is the vector projection of B onto A, and the length here of C is called the component of B with respect to A. So here our textbook uses the notation comp B with respect to A. Okay, and you see that the component here is something which is easy to compute because you see this is nothing else but the length of B times the cosine of theta. So you can also write it in terms of the inner product. So what you have is A times B, the inner product between A and B divided by the length of A. Okay, so this means that the inner product is a convenient tool also in order to compute the lengths of projections. Also the vector C now can be easily computed because it's the length A times B over the length of A multiplied with a vector which has length 1 and is pointing in direction of A, which is given by A over length of A. Okay. So you see that from those two formulas, okay, you see that computing projections is very convenient if you have defined the dot product. And this is essentially also the reason why we look. These are the two important reasons why we look at or why in high school the dot product was defined. Reason number one is a convenient tool for checking whether two vectors are orthogonal or not. Reason number two is it's easy if you have the dot product. It's easy to do projections. Okay. So this was more or less section 12.1, 12.2, 12.3. Now, the next thing which is defined in our textbook is the cross product. Okay, and the cross product is something which only exists in the three-dimensional space. So what you have is you have two vectors A and B in the three-dimensional space vector space over the real numbers. You again introduce coordinates. So let's say the coordinates of A are A1, A2, A3, and of B is B1, B2, B3. Now, one way to define the cross product is just, okay, we say that the cross product is the following vector. This is how we denote it. So we have A2 times B3 minus B2 times A3. Then we have B1 times A3 minus A1 times B3. And then we have A1 times B2 minus A2 times B1. Okay, so this is one way to define it. Okay, you define the if you have two vectors in the three-dimensional vector space over the real numbers, you define a product between those two vectors as this new vector. This is different from the dot product. The dot product is just a number, okay, whereas the cross product gives you a vector. Now, maybe a notation which is more convenient is using determinants. I guess you have also learned this in linear algebra. I guess you know in linear algebra what a determinant is. So what we need is C1, C2, C3. So for this determinant, you know that, okay, this is equal to A1 times this subdeterminant, then minus A2 times plus A3 times B1, B2 times C1, C2. Okay, so this determinant is, okay, you just look at A1, and then you look at the subdeterminant here. So A1 times this subdeterminant minus this one times, you remove this row and this column, and you get this, the remaining subdeterminant is this one, and then you remove this row and this column, and the remaining is this one, and you always change the sign. So this is the definition. You can take this as a definition of the of this determinant here, of this matrix. And if you use this definition, then you have a very convenient way to memorize at least this formula. Namely, okay, so you have the determinant. Okay, so here you have A1, A2, A3, B1, B2, B3. And in the first row, you just have the standard basis vectors, I, J, and K. And if you apply this rule, then you indeed get that the first coordinate here, because this tells you the first coordinate is given by this determinant here, which is computed as this times this minus this times this. So okay, this is this formula. Then the second one is minus the determinant of this, and this. So this is exactly this expression. And the third one is now plus the determinant of this one. So A1 times B2 minus A2 times B1. Also determinants you have learned in linear algebra, right? Right? No? Yes or no? Not yet. Not yet. Then you take this as definition, and how is this defined? So the determinant of those four numbers is defined as A times D minus B times D, C. Okay, so this is the definition. So the determinant of those four numbers, okay, you multiply. It's very easy to memorize. You multiply those two minus those two. Okay, and always the product here minus those two. And for so this would be a matrix of size 2 times 2, and if you have a matrix of size 3 times 3, the determinant by definition, you can take this as a definition. So by definition, is given by this expression here. Okay, I'm not providing in linear algebra. You will learn reasons why, as for why the determinant is defined like this here. I'm not spending time on explaining why, because it's not linear algebra. So just take it as a definition. And if you know this, then it's then a very convenient way to memorize this formula is okay. It's just the determinant of this matrix here. Okay. So the cross product. Everyone has learned the cross product in high school. Yes or no? Not sure why they tell me this is not review for the students. So the cross product is also just review for most of the students, right? Okay, so next time please take a look at section 12.4 and 12.5, because I will spend not a lot of time talking about those two, and then I will go on to things which I assume that they are new. So next time I will maybe spend another 25 minutes to talk about section 12.4, so the cross product, just to review some of the important properties, and section 12.5, and then the remaining two sections, I assume that they will be new for most of the students.